complex exponentials for continuous time signals. Right? So these are complex exponentials for continuous time signals. Okay? So we can define the same thing for discrete time signals as well. Right? So just to sort of stare at this one moment, right? So for continuous time, we have c times e to the power at. Okay? Now in discrete time, we can define something similarly, right? Where we have the signal xn equal to c times alpha to the power n. Okay? Now this is not so much in exactly the same form as before, but you can turn it into the same form by letting alpha be equal to e to the j beta. Okay? So for any complex number alpha, you can always find an expression. Oh, I'm sorry, not j beta, but beta. Okay. You can always express it as e to the power beta for some beta. So in that case, this expression you can also write as c times e to the beta n, right? Which then looks more like what we had before. Okay? So you can definitely do this, but in the discrete time case, we're more accustomed to using this form because then this gives us insights in terms of a geometric series. Okay? All right. Now, again, we can choose c and alpha in general to be complex numbers. But if we start by choosing c and alpha both to be real, then like before, what we get is a real exponential signal that either increases or decreases over time depending on the magnitude of alpha. Okay? So again, right, so here we have a real exponential assuming c greater than 0. Right? Then if we have alpha greater than 1, then as n increases, this signal will blow up exponentially. Right? Now if alpha is between 0 and 1, then as n increases, this will decay. Right? Now what's a little bit different from before is that now the sign of this alpha affects the shape a little bit, right? So if alpha is instead negative, then you will have a sequence that oscillates between positive and negative values. But the magnitude, right, the shape still increases or decreases depending on the magnitude of alpha. Okay? So in fact, if you have alpha between -1 and -1 and 0, then because the magnitude is less than 1, this decays but oscillates between positive and negative. Now, if you have alpha less than -1, okay, because the magnitude is greater than 1, therefore it increases but still oscillates between positive and negative. Okay. So this is when both c and alpha are real. Right. Now, similar to before, we can also consider the case where we pick the exponent to be purely imaginary. Okay? So you can look at this. You can look at this as choosing either beta to be purely imaginary, right? Beta to be purely imaginary, or that you're choosing alpha to be e to the to be an exponential with imaginary exponent. Okay. So in this case, you're looking at alpha with an imaginary exponent. Okay. So this is analogous to the periodic complex exponential signal that we had in the continuous time case. Okay? So let me just say for now, let's call it for now also a periodic complex exponential signal for the discrete time case. Okay? But I want to, sort of put this in gray because saying that it is periodic is not exactly, accurate. Okay? And we'll see that in a moment. Okay? Now, a complex exponential signal like this, by Euler's relation, we can write as cosine omega naught n plus j sine omega naught n. Okay? So this, let's say, periodic complex exponential signal is, again, closely related to a sinusoid like this because we basically have a sinusoid both in the real and the imaginary domain. Okay? So when you look at this complex exponential signal or this sinusoid, you can actually view this as the sampling of a continuous time sinusoid that we talked about before. Right? So for example, if you look at this example here where we have xn equal to cosine 2 pi n over 12, you can view this as samples of this continuous time waveform. Okay? So we can view as the sampling of a continuous time sinusoid x of t cosine 2 pi 1 over 12 t. Okay? And the points that we sample at are integer multiple. The time that we sample at are integer values of this time index t. Okay? So at integer values of t. Okay? So in other words, we're saying that this xn is equal to x at integer values n. So here we're sampling the signal. Okay? We're sampling, in general, the signal cosine 2 pi omega naught t at integer values of t. And in this example here, omega naught is 1 over, sorry. I should use radians for frequency. So here we have cosine omega naught t, right, where omega naught is 2 pi over 12. Okay. So suppose we start from point 0, okay? So suppose that n is equal to 0. In that case, cosine 0 is 1, right? So cosine 0, let's say, is this point here. Okay. Now, when we go from n equal to 0 to n equal to 1, n equal to 2, n equal to 3, all the way up to n equal to 12, right? When n is equal to 12, we find that we get cosine 2 pi, which is again 1, right? So starting from this point, right, if we choose, if this is n equal to 0, then e equal to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, we get back to the same value. Okay? So suppose that this is n equal to 0, which gives you 1. Then after 12 samples, you return back to the same value. And then you start over again. Okay? So this signal, it's easy to see that this signal is periodic. Okay, it's periodic. Now, it's not so clear for this signal, right? Because suppose you start out with a particular point here, then when you go through one cycle of the continuous time sinusoid, you see that in the next cycle of this continuous time sinusoid, we're sampling at a value that is different from this. Okay? Right? So after one cycle, we're sampling at this value that is different from this. Okay? If I go to the next cycle, I'm again sampling at a value that is different from this. So it appears that this is not, it's not immediately clear that this signal is periodic or not. Okay? And the reason is because the frequency we're looking at here is 8 pi over 31. Right, so here, omega naught is 8 pi over 31. Okay? Okay. So suppose you start out with a particular n, right? So let's suppose that this is, okay, let's just imagine that this is n equal to 0, okay? So suppose that you take, let's see. Okay. So suppose that you take 7 samples, right? Suppose you take 7 samples, you get 56 over 31, which is not quite 2 pi, right? So if you start from this point, you take 1, 2, 3, 4, 5, 6, 7, right? After 7 samples, you get 56 over 31, which is not quite 2 pi. So you haven't really sampled an entire period of the sinusoid. But if you go to the next sample, n equal to 8, you have 64 over 31, which is over 2 pi, right? So going from a 7th sample to the 8th sample, you sample over 2 pi, right? You're starting to sample the next period, okay? So after 7, either with 7 or 8 samples, you do not exactly go back to the original point, right? You're either sampling earlier than 2 pi or a little bit later than 2 pi, okay? So from just this period, it's not clear whether or not this is periodic or not, okay? But actually, if you take 31 samples, right, if you take n equal to 31, you will see that we get cosine 8 pi, which is equal to cosine 0, okay? So after 31 samples, we do return back to the same point, and then we start over again, right? It's just that now a period is not as short as the period of the continuous time signal, but actually must extend over multiple periods before we come back to the same point, okay? So even though it's not so obvious by looking at this figure, but mathematically this indeed is also periodic because we can return back after a particular number of samples, okay? But for this signal, right, this is cosine n over 6, right? So the frequency of this signal is 1 over 6. okay? Now, pi is not a rational number, right? So if you want to take an integer n such that n over 6 becomes an exact multiple of 2 pi, this is never possible, right? So for this signal, right, it's actually not periodic, okay? So this is actually not periodic, okay? So this is one thing that it's very different from the continuous time case, okay? So in the continuous time case, the complex exponential with pure imaginary exponent is always periodic. But in the discrete time case, it's not really, okay? Okay. Now again, in general, we can let C and alpha be complex, okay? And then in this case, we follow the same insight as before, right? So if you write, okay. So if you write C in polar form, okay? So that C is equal to the absolute of C times e to the j theta. And you do the same thing for alpha. Okay. Then plugging it into the general formula xn, okay, which is C alpha n, find that this is C times absolute alpha to the power n times e to the j omega naught n plus theta. Okay? So using the same approach, we can see that in general, when they are both complex, we can actually write xn in this form, which is a sinusoid, right? Complex sinusoid, modulated by a magnitude that either increases or decreases with n, depending on whether alpha, the magnitude of alpha is greater or less than 1. Okay. So if you like, you can also expand this into the real part, which is cosine omega naught n plus theta, and the imaginary part, which is sine omega naught n plus theta. So suppose you're plotting out this term here. All right, so if the magnitude of alpha is greater than 1, then you get, right, you get this sinusoid with an amplitude that's expanding. And if the magnitude of alpha is less than 1, then you get this discrete time sinusoid with a magnitude that's decreasing over time. Okay? All right, so this insight is more or less consistent with what we observed in the continuous time case. So any questions up to this point? Now we can look at the periodicity. Okay, we can look at the periodicity of this complex, discrete time complex sinusoid a little bit more carefully, okay? Because this is the main part that differentiates the continuous time from discrete time, okay? So if you recall, in continuous time, when you have this complex sinusoid, right, e to the j omega naught t, we know that the larger this frequency omega naught is, the higher is the rate of oscillation of this sinusoid, right? So if you have omega naught that is larger, then your sinusoid will oscillate faster. If omega naught is smaller, it will oscillate much slower, right? And we also know that this signal is periodic for any omega naught. Okay, any choice of omega naught will make this periodic. Okay, so these are properties of the continuous time case. Okay. Now, in the discrete time case, it just so happens that neither of these properties hold in general. Okay? Now, if we start out from the first property, right? So in continuous time case, we know that if the frequency is larger, the oscillation should be faster. Okay? But if you instead look at the discrete time case, okay, we know that e to the j omega naught plus some 2 pi times n is equal to e to the j 2 pi n times e to the j omega naught times n. And e to the j 2 pi n is always 1. Okay? This is always 1, so this is just e to the j omega naught n. So what does this imply? This implies that this complex sinusoid behaves exactly the same as this complex sinusoid, which has a frequency of omega naught plus 2 pi. Okay? So this tells us that in the discrete time case, this complex sinusoid behaves identically for omega naught that is plus minus an integer multiple of 2 pi. Okay? So this sinusoid with frequency omega naught behaves exactly the same as this complex sinusoid with frequency omega naught plus or minus 2 pi or plus or minus 4 pi and so on and so forth. Okay? So increasing omega naught in the discrete time case does not always continue to increase the rate of oscillation, because eventually when you increase up to 2 pi, you repeat the behavior back again. Okay? So therefore, for the discrete time case, it's sufficient to just specify what happens in between a frequency range of 2 pi, right? Either 0 to 2 pi or minus pi to pi, which are ranges that we often use. Okay? So to illustrate this fact, right, we can look at this example on the next slide. Okay, so here we have, we start with xn equal to cosine